Yeah, welcome back on the third day of this course. So now we get into the last lecture on the signal processing part. We have covered today the propagation effects. So I gave an introduction to all the effects and a little bit of modeling of these effects. And now we finally, after yesterday's discussion on acquisition, we will now take one step further into the refinement of the parameter estimation, and we use this parameter tracking, which is then a gradient method over time to estimate parameters. We will now look at the case of first, we considered the case of time delay estimation in the lecture 2. Then we had a look at time frequencies or time Doppler estimation at the lecture 4, in lecture 4. And now we will consider the problem first of time delay and phase estimation. So during this course, you also have seen maximum likelihood estimator for time delay estimation, time Doppler estimation, and now you will see time phase estimation. And then later we will extend this also to time phase frequency estimation. No? Okay. So GNSS parameter tracking has the objectives first to refine the estimates of Doppler carrier phase and time delay. And secondly, for each satellite based on the initial estimates provided by acquisition. So we further refine now the estimates because acquisition was very coarse, right? We had a sample resolution in time delay and the Doppler resolution defined by these bins, and these bins are not really tight usually, so or close together. So we have like 100 hertz, 200 hertz bins, sometimes larger for the acquisition. Then it has also the objective to track the Doppler carrier phase and time delay for each satellite over time, because these parameters will change over time because satellites are moving and receivers moving. Okay, so then let's have a look now at the maximum likelihood estimator for time delay and phase estimation. So again, as for the other maximum likelihood estimators, we will first define the necessary signal model. You can see here now the Doppler is missing with respect to the last signal model for acquisition. So we consider that the Doppler, for the time being, we consider that the Doppler frequency shift was corrected based on the Doppler estimate from the acquisition. And we will come back to correcting this estimate later. So for the time being, we say, okay, the acquisition provided us a reasonably good estimate. Then in the signal model, and we could correct that already. Then in the remaining signal model X of K, we still have a phase term, which could also be changing over K. I put it here first constant over time. And again, C of tau, which is the sampled and delayed version of the pseudo-random sequence. the noise vector n, and again we are assuming that we're sampling with a duration of ts 1 over 2b. We assume again that n is going from, or is from 0 to n minus 1. K is an index from 0 to k minus 1. Again, we assume that we have more samples per chip than more samples per chip, 2, 3, 4. And we assume that the number of samples per chip is an integer number. And if, and now again, as before, for k equals 0, we can define now dropping this index k. We can forget about this for the time being and say, okay, we have only data for one, the signals only for one period. So we have x, the vector x. This is for x of 0, and this is again the square root of p, the power of the signal, times the expectation with the argument g phi. G of 0, which is the navigation data bit, if any is there at time instant 0, and then we have the PR sequence and the noise vector. Yeah. Again, as before, we can consider a random variable x, where our the received signal x is a realization of this random variable. The random variable has has a multivariate Gaussian probability function, density function, as given here on the top, and we can see now that this PDF is parameterized by the time delay and the phase. Again, the likelihood is equivalent to this PDF, and the likelihood is considering one realization. We're trying to find the parameters tau and phi that are best matching to this realization, and we can estimate these two parameters now by maximizing the likelihood with respect to tau and phi, and it's equivalent to maximizing the log likelihood because the logarithm is a monotonic function. Okay, so this we already did that twice. Now this is a slightly different problem. So we can apply the natural logarithm here, and we can drop several of these terms, arriving here at this equation here. Where's my hand? Here. Arriving at this equation here. The first three terms are not dependent on the parameters that we are estimating, so not dependent on tau or phi. So we can drop them, and we can assume that, as we did before, that the L2 norm square of the sampled PR sequence C is equivalent to, or approximately n, as well as we can also drop the factor 2 square root of p, and that's then we end up with maximizing over the real part of x, g of 0, the exponential function with the argument j phi, and the sample delayed version of the PR sequence. So now let's look into this further, developing this. We could, for example, now take the derivative of the log likelihood with respect to the phase, because we're looking for a global optimum, and at this global optimum, the derivative with respect to the different parameters should be 0. So we can use this to build some equations, formulate some equations. So we can build here now or derive the derivative with respect to the phase. So we end up with minus sinus phi, the real part of G0 x Hermitian C of tau, minus cosinus phi of the imaginary part of G0 x Hermitian C of tau. And when we equate the above derivative to zero, we get something that is quite well known. If we want to extract the phase here, then we have the tangent of the phase is equivalent to the imaginary part of the cross correlation x Hermitian C divided by the real part of the cross correlation of x Hermitian C, and we take the negative of that. And when we now want to estimate phi, we have to take the Arcus tangent of this of this ratio, so minus the imaginary part of the cross correlation divided by the real part. That's nice. We have now an estimate of phi. We can plug this in again into the log likelihood. It's getting a little bit cumbersome now. But we can resolve that. So we start further developing the log likelihood, and this is what we call the concentrated criterion. So the LC likelihood concentrated. So the real part of this exponential function to the power of j, and then the Arcus tangent of the imaginary part of G0 x Hermitian C of tau divided by the real part of G0 x Hermitian C of tau times G of 0 x Hermitian C of tau, and we can rename this argument or in the Arcus tangent and call that psi. Yeah, and so you have a better, a simpler writing, and then we end up here at the end. At the bottom, we end up with the real part of 1 over the square root of 1 plus psi to the power of 2 plus j psi divided by the square root of 1 plus psi square. And we used here these theorems that are cited in the bottom of the slide, so that the cosine of arctangent phi psi is equivalent to 1 over the square root of 1 plus psi square, and that sinus of the arctangent psi is equivalent to psi over the square root of 1 plus psi square. Applying all this, we can reformulate the whole thing to real part of G0 x Hermitian C of tau minus psi times the imaginary part of G of 0 x Hermitian C of tau divided by the square root of 1 plus psi square. This looks much better now, so we can work with that. So let's keep on working. We can now include again this ratio for psi, because psi is equivalent to minus the imaginary part divided by the real part of G0 x Hermitian C of tau. Can include that again. And after some reformulation, finally and thankfully, we arrive at something very simple, which is that the concentrated log likelihood function is equivalent to the absolute value of x Hermitian C of tau. After so much work, this is a great relief that we have a nice result. So the estimator for the time delay, we can formulate this now as tau hat being the argument max of x Hermitian C of tau, and the absolute value, we can also take the absolute value square. It doesn't matter. So this is nice. And if you remember, we had the same result already in the beginning of the course when we talked about time delay estimation only. And now you can see how this now, we try now to link this to the delay lock loop and to the phase lock loop. So let's start linking this to these tracking systems. If you remember back from the lecture 2, we already used here the gradient ascent method. We do that again. In practice, we maximize x Hermitian c of tau, and we use the square, and this is what's then called a non-coherent, so we will now derive a non-coherent delay lock loop. It's also interesting to note that the non-coherent delay lock loop together with a phase lock loop is kind of equivalent to or is an implementation, is a possible implementation of a maximum likelihood estimator, joint estimator for time delay and phase. So we use the results here that we already applied for the gradient ascent method as before, and we get tau hat of k at time instant k is equivalent to tau, the estimate of the time delay at the previous time instant, and we use here a plus. We have a mu tau, which is this, it's called step size, and then we calculate the gradient of the concentrated log likelihood, considering the estimate of tau at k minus 1. And now we can, instead of using the derivative, we can approximate this with the central difference quotient as before of length 2 delta. And then we can plug in here this this approximation. So we have tau hat k minus 1, mu tau divided by 2 delta, and then we have this difference of a delay plus delta using a tau hat k minus 1 plus delta and tau hat k minus 1 minus delta. If we now plug in the what we derived, what is the log likelihood of what is this, the logarithm of the concentrated likelihood, then we can see here in the end, we get to x Hermitian c of tau hat k minus 1 plus delta, and we take the absolute valued square minus x Hermitian c tau hat k minus 1 minus delta and take the absolute valued square. Okay. Yeah, and to derive the central difference quotient, the DLL uses a correlator pair, as we have seen. These two correlators are called early and late correlators. You can find that in any literature on delay lock loops. To obtain the gradient method using a feedback structure, we consider that the observations are successively collected in intervals with xk. So now we're moving to a stochastic version of this feedback system, considering data changing over time and also parameters changing over time. We also take into account that the parameter tau k is not deterministic anymore, constant over k, but changes with different time instances k according to the satellite motion, user motion, and propagation effects. And thus, in the end, we can now write an equation for the updating the time delay estimate or refining the time delay estimate, because we will start with we initialize this process with the time delay estimate from the acquisition, and then we can gradually refine this estimate and follow the changes of this parameter tau over time with this feedback system. Or feedback structure as written in the title. Yeah, we also need to estimate the phase. The interesting part that we have seen is that the phase and the time delay can be estimated independent of the phase estimate. The phase estimate now is based on the time delay estimate. So to derive a feedback structure for the phase estimate phi hat with a phase locked loop, PLL, we can use now the MLE of the phase and also use a gradient structure. So we have phi of phi hat of k is equivalent to phi hat of k minus 1, so the previous iteration, and we can now gradually update this with this Arcus tangent here of the imaginary part of x Hermitian k minus 1 times e to the j phi hat k minus 1 times c tau hat k minus 1. And we divide that to the real part of this thing and take a minus, and with this we can gradually update the phase estimate and also follow the changes of the phase over time. This also depends how well we can follow the changes over time. Is dependent on this step size mu phi here. Yeah, so now let's, we have shown how we can derive an implementation of a delay lock loop and a phase lock loop starting from the max joint maximum likelihood estimator for time delay and phase. We could also use a Bayesian estimator and derive the delay lock loop and the phase lock loop from this. I choose this way. Starting with the assumption that the parameters are not changing over time and are constant to a feedback system, but you can arrive at the same result. Yeah, so here's a block diagram now. What happens in a non-coherent DLL? We can clearly see we have these two branches of correlation, the early and the late. In the input, so you have to be aware, because this is maybe different to other sources in the literature. I work with the conjugate of X. So because so the input signal, we take the conjugate of that. This is because we always ended up with this formulation of X Hermitian times C. This was our definition of cross correlation. You have to be aware that this is a little bit different from the other literature. I decided to stick to the conjugate here. So what we do is we conjugate the input and then we move on with the processing here. So this is just the first two branches here. We multiply with the reference sequence C. One is delayed by tau hat k plus plus delta, and the other one is delayed by tau hat minus delta, early and late. So early is the upper branch and late is the lower branch. And then we sum up. This is correlation. Take the absolute valued square, and we take the difference. This is the implementation of the central difference quotient. And then we have implemented quasi only the correction term, which is called here discriminator. So we have an error function here, e to tau of x, and this is equivalent to ps, and this is the S curve of a non-coherent delay lock loop, dependent over time, so k, and parameterized by the tracking error epsilon tau of k, and remember the tracking error was tau minus tau hat, plus some noise, some discriminator noise, which would be then the noise of the early branch minus the noise of the the late branch. And then this error signal passes through a loop filter, which is f tau of z, and the output of the loop filter enters an integrator. So we are integrating these difference estimates over time, and this accumulates to the time delay estimate at time instant k. So we accumulate the changes of the time delay of the delay lock loop, which is described by the discriminator over time, and this then accumulates to the current estimate tau hat, which is then used in the correlators again to create a new value of the discriminator. Yeah, the S-curve for the non-coherent DLL can be given by this term given here. So we have the autocorrelation function of the of the tracking error epsilon tau. Below in the bottom you can see, so epsilon tau of k is equivalent to t of k minus tau, tau of k minus tau hat of k. And these correlations, so the the early correlation is defined as 1 over n, the sum of n to 0 to n minus 1, and then the correlation between the received signal and the model, and the model is here using the delay tau hat plus delta, and for the late correlation, we use the model with tau hat of k minus delta. And here we assume again the S-curve. This is the S-curve without clearly without noise, yeah. And we assume again that the model that we use in the receiver is perfectly matching the signal. That's why we have here C correlated with C, and that's why we can talk about we can use the autocorrelation function of C to formulate the S-curve. In practice, this is, as I mentioned several times already, this is not the case. We do not exactly know the signal characteristic coming from each satellite. We know a definition of this characteristic coming from the signal in space ICD interface control document, but this is not exactly how the signal looks like that's coming from the satellite, but very close. Yeah? And I told you that due to this mismatch of knowledge in the receiver and the signal that is transmitted, we have some biases that are called receiver biases in the literature, and that we have to correct. We can find some information from services that help us to correct this, or we have to kind of estimate them together with positioning also. This is possible in a precise point positioning approach. Yeah, and the noise, I just show how we can formulate the noise. So the noise component n tau, so the discriminator noise of the error signal E, and this needs to be E tau, I'm sorry, can be decomposed into n tau, and this is equivalent to the noise in the early branch minus the noise in the late branch. And I just give here the formulation of it, and while n tilde of E is as a correlation with the model with the noise in the early branch, and n tilde of L is the correlation of the receiving noise or receiver noise correlated with the late branch. Yeah, so you see the noise is also dependent on the distribution of the phase a little bit. Yeah. The mth order loop filter, F tau, is a so-called higher order weighted integrator usually, and can be given as, with this formulation here, you see, we can define these coefficients alpha tau m for this filter. So this is how to specify the filter. And we here use the z function, the z transform of f of tau of k is f tau of z. An estimate of the time delay at time instant k can be given by, so we have the output of the loop filter times kg tau, which is the coefficient of the integrator, and ut, if you remember, was the u tau, if you remember, was the signal at the output of the loop filter. What does the loop filter do? It should reduce the noise drastically, and then the integrator is integrating the changes of the discriminator signal. And we can give here the transfer function of this integrator, deriving here from this time delay estimate, and the transfer function then of g of tau of z is the Fourier transform, or the Z transform of tau, so tau hat, so t hat Z divided by the Z transform of U of tau. And this is then kg tau Z to the -1 divided by 1 minus Z to the -1. And we see clearly that this is an integrator characteristic, while we can also use the Z transform to derive a time response of this filter or integrator. I will be very generic here about the loop filters and the integrator. We have a lab class today where we will design some of these filters. So in the afternoon, further in the evening, we will work on that a little bit. So now let's move to the PLL. We have the DLL. We saw that the non-coherent DLL is not dependent on the phase, so it can kind of run autonomously without the other estimates. However, we need the estimate tau hat of k to produce a new model signal to generate a correlation with this tau hat of k, which is then in the literature always called the prompt correlator, to derive the phase estimate. So besides the early and late correlator, as I just said, included in the DLL, the PLL includes the so-called prompt correlator. And in this block diagram here, we can see that the DLL is providing this reference signal C of kn plus n parameterized by tau, so delayed by tau hat of k to the PLL in our model. And by doing so, we can see here on the top, coming from the top quasi, this reference signal. So we multiply now the input signal with this reference signal, and we sum up these sample by sample, which is implementing correlation. The multiplication of the reference signal with the conjugate of the received signal. So before the multiplication, now we have realized a correlation also. So this is then prompt correlator output. And then we multiply this prompt correlator output with the current phase estimate in an exponential function. Pass that into the Arcus tangent, and we have a minus here. This is maybe disturbing some of you because you know from the literature the minus is not there, but this is it. The minus has to be implemented because we are working here in this class with the conjugate of x. And that's why the minus appears inside the Arcus tangent discriminator or Arcus tangent discriminator. At the output of the Arcus tangent function, we have then also an error signal, E of phi, and we have here epsilon of phi, which is the phase tracking error. So this is phi minus phi hat. And we have some noise, discriminator noise. This enters again as for the DLL to a loop filter phi, f of phi of z, and then into an integrator g of phi of z. And this structure that we have here is called a Costas PLL, and nicely it is also insensitive to navigation message bits. So whenever they change, they don't disturb the phase estimate, because they change over time and we don't know them. But in the Arcus tangent, as we are dividing the imaginary part of the prompt correlator output, multiplied with phase correction by the real part, and as the symbols that we receive are real, so they're -1 or 1, they disappear inside of the Arcus tangent in the argument, and so the argument of the Arcus tangent is already independent of the navigation message bits, and so the output, the error signal, is also independent of these message bits. So the PLL can just continue tracking no matter if you receive message bits or not, no matter if you are tracking a pilot signal or not. Yes, and again, the mth order loop filter can be given here as again as an integrator or higher order integrator. Now we have the filter coefficients A, phi, m. An estimate of the phase at time instant k then can be given as phi of k minus 1 plus k g phi u phi of k minus 1, and u phi of k minus 1 is the output of the loop filter. And using the z transform, we can transform the equation, this equation to the z domain, and then we have phi hat of z is equivalent to phi hat of z minus 1 plus kg phi u phi of z to the minus 1. And now calculating the transfer function, which means we are dividing output by the input signal, we get kg phi of z to the minus 1, 1 minus z to the minus 1, which is an integrator again. So we're integrating the discriminator over time, and the loop filter is trying to remove as much as possible the noise before integrating these discriminator values. Yes, and now we will turn our attention back to the Doppler frequency. I mean, we started out in the beginning of this lecture that we assumed, okay, the Doppler is well estimated and it's corrected, and this estimate's coming from the signal acquisition. But yeah, what's the case when this is not perfectly estimated? So we would, and maybe the Doppler, or definitely the Doppler is changing over time because the relative movement of the satellite with respect to the users is changing. So the Doppler is changing over time. So we have to track also the Doppler shift. And I would like to stress here again, the shift is just a model. So we apply only the Doppler correction with respect to the assumption that the Doppler frequency, so the relative movement of the satellite and the user is much, much, much smaller than the speed of light. And with this kind of the dilatation effect then of the Doppler effect can then be modeled by a shift. This is what we do. We have to be aware of that. So yeah, and the acquisition, I think I mentioned most of this already. So the acquisition provides an initial estimate of the Doppler shift. This initial estimate in general is not exact enough, or as the satellite, yeah, as I said, this receiver is moving, the Doppler shift is changing over time. The estimate of the Doppler frequency shift needs to be refined and adapted over time, and that's why we talk about Doppler tracking also. And the Doppler estimate can be refined using a feedback structure, and we will derive now this feedback structure, and the Doppler frequency shift, including the Doppler phase, we will learn in the next slides what this is, are corrected before feeding the signal to the DLL and the PLL, because that's important. We need to feed back minimum the Doppler frequency and the Doppler shift, the phase of the Doppler frequency in the considered time interval, in order to correct this Doppler frequency by means of our reference signal, in order to maximize cross correlation. That's important. So for the DLL, we have to maximize cross correlation. So the DLL is dependent on the update of the Doppler frequency shift. So because if the Doppler is changing over time and is changing very rapidly over time, and we are not correcting this, the cross correlation can decrease and decrease and decrease, and the DLL will lose track. So we at minimum have to feed back the Doppler shift, and as we are working in a block system, we also have in a blockwise system with correlation, we also have a phase of this Doppler frequency that we also need to derive and feedback minimum. There's also the what we called here phase, which is in general the Doppler phase plus the phase that we considered here is then the carrier phase. And And in our implementation here, we are not feeding back the carrier phase, the total carrier phase, but this is also possible. You could also take the output of the PLL and derive also the Doppler changes and also feed back the output of the PLL. But we are not doing this, not necessary to do this for the non-coherent, as we are applying a non-coherent DLL. So the PLL in our case is fully separated, running fully separately from the DLL, and we will derive also a feedback structure for the Doppler frequency, which will be a frequency locked loop, so an FLL. Yeah, the Doppler phase is updated for each period k with duration td, and we will see that this is very simple because the Doppler phase can be derived by the integral over the Doppler frequency over the time over the integral integration time. Yeah. So let's have a look at this structure by means of a block diagram. So we have the DLL, the PLL, we already understood that. Now we have additionally an output from the PLL. So we have the prompt correlator output, we see that. Also going to the FLL, and we will derive in the FLL an estimate of the Doppler phase phi nu plus the Doppler frequency nu hat. Yeah, and then we will feed that back to an exponential function, and this exponential function for each time instant n will correct this Doppler frequency, including the phase from the received conjugate signal, and this corrected Doppler signal will enter now the DLL, PLL, and FLL again. Yeah. However, the phase estimate phi hat, this includes all the propagation effects and also of the phase, and also the information about the bit transitions and all these things. And this is derived, dependent on the Doppler and Doppler phase and time delay estimate, but this phase estimate is not needed for the FLL and is also not needed for the DLL specifically. Yeah, how can we derive a Doppler frequency now? We can use the initialization of the acquisition, and then we can further refine this frequency by using the time derivative of the phase, yeah, because the derivative of our phase phi includes or by a derivative of the phase of the, which is then the phase of the output of the prompt correlator, yeah. And if we derive this phase with respect to time, take a derivative, then we end up with a Doppler, the residual Doppler frequency. Yeah, and this is how we can put this here. So the estimate nu hat is the residual Doppler, or is the included Doppler frequency based on the derivation of the phase over time. And here it's 2 pi td, so one duration of the PR sequence. Introducing the MLE of the phase, now we can give here this Arcos tangent, and then we have the phase estimate kind of based on a formulation of the prompt correlator output. And alternatively, we can also write this as tangent of phi hat k minus phi hat k minus 1. Yeah, so we can alternatively write tangent phi hat k minus phi hat k minus 1 as tangent of phi hat k minus tangent of phi hat k minus 1 divided by 1 plus tangent phi hat k times tangent phi hat k minus 1. And now we can use that in this formulation above and introduce this, as you can see here now. by using that tangent of minus x is equivalent to minus tangent of x. And we arrive at a very nice formulation where we get phi nu hat of k being equivalent to the arcus-tangent of qk ik minus 1 minus qk minus 1 ik divided by ik ik minus 1 plus qk qk minus 1 divided by 2 pi td. And this qk is the imaginary part of the prompt correlation, and ik is the real part of the prompt correlation. And with this, we can refine Doppler estimates. And this is what we can do now in the DLL, in the Doppler feedback system. Additionally, we have to estimate the Doppler phase, because the Doppler frequency in our time interval is not starting with 0. So we have a phase dependent on, and it's dependent on time, but we can easily estimate it because in principle this phase is the integral over the Doppler frequency over with respect to TD, and we can put this here. So nu hat k times TD times 2 pi. Plus the estimate of the Doppler phase from the previous interval is the Doppler phase of the next interval, and the Doppler phase in this estimation process can easily be initialized with 0. We could also estimate the Doppler phase from acquisition, but it's not necessary really. The convergence of the Doppler phase estimate is quite okay with the assumption of 0. And the Doppler phase estimate also includes changes of the Doppler frequency over time. So now we have Doppler frequency, Doppler phase. And we can now put this together into a loop or feedback structure. So we see here we have the prompt correlator on the left-hand side and the reference code coming from the DLL for the prompt correlation coming from the top. Then we have the feedback here from the correction from the previous estimate. Then we sum up here and we create correlation. So the prompt correlation, and then this is included into is passing to the discriminator, which is this arctangent discriminator. At the output we have an error signal. We have the Doppler tracking error, which is mu k minus mu hat k, and discriminator noise. Again, we have a loop filter, f nu of z. We have an integrator, g nu of z. And we have that this FLL is insensitive to navigation message bits again, because everything is based on phase estimates, and the phase estimate already was independent on message bits. So this is nice. Again, we can estimate, give here the loop filter. They have all the same structure. So there's always a higher order integrator. The loop filter has always the same purpose in all these loops to minimize the noise. And then we have the integrator. Again, this has the same structure as for the DLL and the PLL. We can use the Z transform as we are in a discrete domain. The Z transform here, N hat is the Z transform of nu hat. And we can then also again derive the transfer function of the integrator, and it's the same. We just have a different gain coefficient, k, g, nu, z to the minus 1, 1 minus z to the minus 1. And so this is an integrator again. Yeah, and now we can look at loop transfer functions, and we need the loop transfer functions. So we have defined delay lock loop, DLL, phase lock loop, PLL, frequency lock, FLL. I have shown you how these three loops work together. It's possible also to skip the FLL and only use a PLL in this structure, but I prefer to use this three loop structure in this talk. Now let's talk about transfer functions in the last 4 slides. Transfer functions are important to characterize behavior of the loops, and I will just show them briefly, and then in a sort of self-study, you can go on using these and exploring these. Yeah, for the non-coherent DLL, the estimate of tau hat, the estimate tau hat k of a non-coherent DLL based on an error signal without discriminator noise can be given now here as in time domain. Yeah, so we have the integrator G of tk convolved with the loop filter convolved with the error signal without noise. And when we linearize the S curve, we can now linearize that. What happens here, we take the derivative of the S curve at tracking error 0. Yeah? This is this S prime n k of 0. This is the second equation from the top. And we multiply then with the tracking error. This is a very simple linearization. We take the derivative or the slope of the S curve in 0 multiplied with the tracking error. And we rewrote the tracking error here with tau k minus tau hat k. Yes, and then we can take the Z transform here and we can derive the loop transfer function after linearization of the S curve for the delay lock loop, for a non-coherent delay lock loop. And we can see that this transfer function, which means is output divided by input. So, or the transfer function of the estimate with respect to the true time delay. And this is then the power times the slope of the S curve at 0, the integrator and the loop filter divided by 1 plus P, and then slope S curve at 0, integrator loop filter. So you can use this transfer function then to evaluate how does the estimate behave when the true time delay, for example, is changing with dynamics or anything. This is very interesting to understand this. You can also add noise to this transfer function and see how the estimate behaves with noise and so on. So this is good to analyze the behavior and especially the transient behavior of the delay lock loop. We can calculate also, this is, I can show you here how does the S curve of a non-coherent delay lock loop for a rectangular chip pulse, or for example, GPSCA or Galileo E5B look like with delta, so with a and then this is called we call that this delta was related to the implementation of the central difference quotient. In the literature, this is then called the early-late spacing or spacing, correlator spacing. It's not the early-late spacing, it's the correlators, because the early-late spacing would be 2 delta. And this is now here 0.5 chips, and with this approximation through the central difference quotient, we can see that we have a large linear region of the S curve, and then we have a nonlinear region. But in this nonlinear region, the loop would not converge as we have implemented it, right? So the loop in this central difference quotient approximation only can converge to zero tracking error in this linear region. And that's why we used also the linearization. If the tracking error gets too large, it will diverge either to the right or to the left. So it will lose track. This is exactly what happens when we lose track, when the parameter is either changing very fast over time and the loop cannot follow based on its design of the loop filters, or if the noise is so large suddenly that we're drifting too much to the right or to the left, and we are leaving this linear region, and the loop is diverging, and we have lost track. In the receiver, usually we need something that will detect that. So we need to implement what's called a loop, lock detector. So we need to understand, are we still tracking a signal, or have we already lost the signal, and are we diverging, following the noise, or with our correlation? But this is easy to implement because you can also look at the carrier to noise density estimate based on the prompt correlator. And then you easily see, oh, this is getting really small. So, okay, we have maybe lost the satellite. We have to go back to acquisition, reacquire, start the loops again. Yeah, we can also derive the transfer function for the PLL. We do the same thing. So we consider the Arcus tangent discriminator, so the Costas PLL, and without noise, we can pass now the error, the phase error to the through the filters, and we can calculate that in time domain by the convolution. We can apply the Z transform now, and we can see that we can derive a transfer function for the PLL very simply, and this is only dependent on the integrator and the loop filter. Again, we can use that to model and assess the transient behavior and also the noise behavior of the loop. And we can do the same for the FLL, and we get the same structure as for the PLL, but with the integrator and FLL loop filter here. So I will stop here for today because we have not much more time to go on with the signal processing. There's a lot of details we could go on, but I think you got in these first 6 lectures a good overview on signals, signal properties, what kinds of signals are used. I hope you could also get an overview of why are the signals designed like this, what's the idea behind this. We have also learned about propagation effects that we have to consider. We have learned, okay, how does the receiver work with acquisition and tracking? We have seen that this is a 2-step estimation of parameters. Which parameters are we estimating? Time delay, phase, and Doppler. We could also estimate amplitudes, and not a big deal if we already have the 3. The amplitude can be calculated in closed form. Yeah, we did not touch the navigation message, bit detection, and decoding and these kind of things, but the phase estimate, so the output of the FLL in our case, is very important for creating a prompt correlator output that is Doppler phase and phase corrected, and then we can afterwards detect the message bits and then start with the decoding. In case of GPSCA code, we don't need to decode. There is no code, but in all the other signals, we have then to look into decoding. So yeah, I hope I could introduce the signal processing to you. Tomorrow, my colleagues from UPC will start with the data processing. No, tomorrow we have the local talks. Yes, this is right. On Friday, they will start with the data processing, and this will continue until next Tuesday. So stay tuned here. Tomorrow we have two interesting talks that are linked to GNSS and that bridge the gap between GNSS and remote sensing. Very interesting talks from UFIC, from Labomar, and from the president of FUNSEMI. So also join in tomorrow. We have also we have our visit to INPE tomorrow here to the local site of the Brazilian Space Research Center in the afternoon. For you online, unfortunately, we cannot take you there, but we'll have a talk there also from one of the researchers. We might make that available after the workshop. So thank you very much. If you have questions on this lecture 6 here in the room or in the chat, we have no questions in the room. So thank you very much. Take care.